Welcome to the class. So let us start with the revision of last lesson, electric current. So I said electric current is the time rate of flow of electric charge. Time rate of flow of electric charge. That is the flow, the rate at which the electric charge flows through wire or through a circuit. So that is what is called electric current. If the rate is high, we say the current is high. If the rate is low, we say electric current is low. So the rate, so the current, so the formula of current will now be quantity of electric charge over time taken. Quantity of electric charge over time taken. Now look at this I. The symbol of electric current is I, and Q is the quantity of charge. The unit is coulomb or capital letter C. Coulomb in capital letter C. Okay. The unit of current is amperes. Amperes or capital letter A. Then the unit of time is in seconds. Okay. Now, ampere. And the instrument used to measure current is called ammeter. It's known as ammeter. Look at the diagram here. This is an ammeter, an instrument used to measure currents that flows in a circuit. So we have different calibration. This one is from 0, 5, 10. We have some that are 0, 1, 2, 3, some 0, 0.5, like that. So they are calibrated in different ways. Okay, so this is ammeter. This is the one we are using in the lab. It's ammeter. So you see, this one is calibrated in 1, 1, 1. Calibration is 1, 1. And see it. Okay. And the symbol is this circle and A. This is the symbol of ammeter. When you see this in an electric circuit, it means ammeter must be here. Ammeter must be in this place. We are going to measure the current flow in this part of the circuit. So the formula is I equals to Q over T. Take note of this formula. All right. So we want to make use of this formula now to calculate. If we know the quantity of electric charge that flows through a circuit, then we can calculate the current through that circuit. And also the time. When we're talking about time rate, it will take time to do. Okay, it will take time. I is Q over time. All right, so let's look at this question now. Let's look at this one. A charge of 30 coulombs flows through a wire for... Okay, now a charge of 30 coulombs flows through a wire in 5 seconds. What is the current? What is the current? So the charge here is 30 coulombs, 30 coulombs. So the unit of electric charge is coulomb. Okay, now through the wire for 5 seconds. Time is 5 seconds. Then you have to use the formula. From the question, we have the quantity of charge equals to 30 coulombs, and the time taken for the flow is 5 seconds. 5 seconds. So what is now the current through that wire? Current that flows through the wire. So the formula is I equals to Q over T. I equals to Q over T. Okay, now Q equals to 30. So now so when you substitute, I is the current will now be 30 divided by 5, because Q equals to 5. Q is equals to 30 and time T equals to 5. T equals to 5. So the current will now be 6 ampere, because 30 divided by 5 equals to 6. That will be 6 amperes. Okay. Now let's look at the other one. An electric circuit has a current of 4 amperes. How much charge flows through the circuit in 10 seconds? Okay. From this question now, the current is given 4 amperes, and you have to calculate the charge that flows in the 10 seconds. Okay. Current is given 4 amperes, then time is given 10 seconds. So then so we are calculating Q, that is quantity of charge. Q is quantity of charge, quantity of electric charge. Okay, from the formula say I equals to Q over T. So current will now be, the current, okay, current is given. The current is given. So 4 equals to Q is not given, over 10. This 4 is 4 over 1. When you cross multiply, Q equals to 4 times 10. And Q equals to 40. The unit is coulombs. 40 coulombs. It means 40 coulombs of electric charge will flow for 10 seconds if you are to have a current of 4 amperes. Then the next one, if a current of 2.5 amperes flows through a circuit for 8 seconds, calculate the total charge that has passed. So I is 2.5. So current is 2.5 amperes. The time taken, T, is 8 seconds. 8 seconds. Then the quantity of charge, we don't know. So that is what we are calculating. Now write the formula. I equals to Q over T. So 2.5 is I, equals to Q, we don't know Q, over 8. Then, you see, from this, when you cross multiply, this is 2.5 over 1. When you cross multiply, Q equals to 2.5 times 8. So the quantity of charge will be 20 coulombs. 20 coulombs. So that is the quantity of charge there. Okay, let's look at another one. How long will it take a current of 3 amperes to transfer a charge of 24 coulombs? How long means time. You have to calculate time. T, you have to calculate time. Okay, then you are given the current, 3 amperes. We are given the quantity of electric charge that flows, 24 coulombs. So the formula is I equals to Q over T. So that is 3 equals to 24 over time. It's time we are calculating now. When you cross multiply, you are going to have 3T equals to 24. Now let's divide both sides by 3. So the T now will now be 3 here, 1, 3 in 24, 8. So it's going to be 8 seconds. 8 seconds. So let me quickly give you the last one before we continue. Yes, a device allows 15 coulombs of charge to flow in 0.5 minutes. Find the current in amperes. I told you that if you are given time in minutes, it must be converted to seconds. So we are given 0.5 minutes, that is half minute. Half minute equals to 30 seconds. So let's start. A device allows 15 coulombs. So you are given the charge. Q equals to 15 coulombs. That is the quantity of charge. Then time is 0.5 minutes. 0.5 minutes, which is equal to 30 seconds. 30 seconds. So 0.5, half minute is 30 seconds. Then we are now to calculate the current. Okay, let's now calculate. Let's use the formula. Formula we're using now is formula is T I equals to Q over T. Okay, and I equals to 15 divided by 30. So the current will now be 0.5 ampere. So 0.5 ampere. So this will be the current in through that device. So I want to believe that you now you should be able to solve simple problems on electric current. So as you know that electric current is a quantity of electric charge per time. Quantity of electric charge per time, that is the rate of flow of electric charges. Time rate of flow of electric charges is known as electric current. Electric current. Okay. Now, I gave you some questions to do. Look at it. You have this question. Go through it, and you should be able to do it. All the parameters are there in question one. You are given Q, and you are given T. You have to find I, current. In question 2, you are given current. You are given time. You have to find quantity of electric charge. That is Q. In question 3, you are given current and the quantity of charge. You have to calculate time. So it's very simple. In number 4, you are given I, that is current, and you have to calculate Q in 1 minute. 1 minute is 60 seconds. You are given time. You have to calculate Q. And number 5, you are given current, and also you are given time. You have to calculate Q. It's very simple. You have the formula with you. And also the next question from number 6 to number 10. Number 6, you are given charge, Q. You are given time is 0.5 seconds. So you have to calculate I, which is the current, which is I. Also, number 7, you are given current. You are given time. You have to calculate Q, which is charge. Number 8, how long means time. You are given current and you are given charge. You have to calculate time. Number 9, you are given charge and time. You have to calculate current. And number 10, you are given charge and time. You are also to calculate current. So current is I. Whenever you say I in physics, under electricity, it means current. And Q is quantity of electric charge. While T is time. Okay. So I will be expecting the solution as soon as possible. Now today, I want us to go into other important aspect of electricity. After that, I've explained electric current as the flow, the movement. So electric current has to do with flow of charges. So that is when electrons are also known as charges, when they move from one point of wire to the other, then what is called current is produced. Current is produced. If they have not moved, nothing like current. It is their movement, it is the motion or the flow, we call it the flow, that determines that produces what is known as current. And if the motion is high, if the flow is high, if the rate of flow is high, then the current is also high. If the rate of flow is low, the current is low. Do you understand? Okay. But today, Let's look at another important quantity that we need that is very important, and it is called potential difference. Potential difference or voltage, simply voltage. We say voltage, current, voltage. What is now the difference between current and voltage? Now I want to explain to you the relationship between current and voltage. What is potential difference? Potential difference is work done to move a unit charge between two points in a circuit. Is the work done to move a unit charge between 2 points in a circuit. Okay, that is when you have, when before charge can move from one point of a conductor, let's say from one point of wire to another point. Okay, let me let's have wire now. Now let's have point A and this is point B. Before electrons or before charges can move from this point A to point B, something must cause it. Something must cause it to move. That thing is called potential difference. Is the work done to move, because it has to do with motion. That's why it is termed work done. Okay, something like a push. Potential difference is like the push that make current to flow. So I would say a high voltage give a strong push. When we say the voltage is high, if the voltage is high, then there will be a strong push. We are going to have more charges flow per time. But if the voltage is low, then we are going to have the push will not be high, will be low. There will not be more strength, more power to push, more energy to push the charges to flow. That is why the more the potential difference, the more the current. If the potential difference is low, current will also become low. Okay, so it is like a push. I tell me it's like the push. Look at it here. I said it is like the push that makes current flow. The push that push the electric charges to move from one point of the conductor to the other. The electron cannot just move. Electrons or charges will be produced. Under static electricity, charges are produced. So I've explained that the three methods of producing electric charges. After those electric charges have been produced in a conductor, something needed to push it to flow, cause it to flow. That thing is called potential difference. It's also known as voltage, and we use letter V to denote voltage. Whenever you see V, it means potential difference. So it is the work done. It is a push. Something that will cause the electric charge to move from one point to the another. So we can now say the relationship between voltage and current now is that voltage is directly proportional to current. So I want you to have the understanding that the more the voltage, the more the current. If the voltage is high, the current will be high. So that is why we say it interchangeably. It's not you say, the current is low, or you say the voltage is low. It's right. Both are correct. Because if current is high, if voltage is high, current will be high. Of course, it is the voltage that determines the magnitude of the current. It's the voltage that determines the magnitude of the current, not the other way around. You can't say we have the high current, we have high voltage. No. If you have high current, it means we already have high voltage. So the potential difference, from if there is, the more the potential difference, the more the flow, the more the current. So I need you to understand that. So it is the work done to move a unit charge from one point in a circuit to the other, between 2 points in a circuit. You understand? So it's like a push. Just understand it like a push. Charges are produced, but something that will now begin to push. Then as it's pushing, then they are moving. So the more the flow, the more the push, the more the flow, then the more the current. So I believe you understand that now. Now there is an instrument used to measure potential difference of voltage, simply voltage. The instrument is called voltmeter. The instrument is called voltmeter. So you see it here, this voltmeter. I want to give you the show you the one I have here. This one I'm using in the lab. So it has terminals here. So we need to see it. When you see the one written V, for ammeter, A is written inside here, but for this one, this is V, voltage. So that's how to differentiate between the two. And look at this symbol here. The symbol here is V. See this circle and V inside. It means voltmeter. It means voltmeter. The one under it here is ammeter. You see it is A, and this is voltmeter. Okay, I need you to understand that. So gradually you are getting to know the symbols of electrical components. And as we continue, I'm still going to give you, I will show you other electrical components that we have. So other electrical components, I will show you these electrical components we have in there. So, and their symbols, show you that so that it will help you. So by the time you see them in the circuit, what you are seeing here is called electric circuit. When we get there, I'm going to explain what electric circuit means. I'm going to explain everything to you, but I want you to just understand each symbol, one after the other, as we continue. So for voltage, we use voltmeter to measure it. So the more the voltage, the more the current. Okay. All right. The formula is V over W over Q. That is work. The W you are seeing here is work. That is work per unit charge. Work per unit charge. Q is charge. W here is work. And V here is voltage. Okay. All right. The unit of electric potential difference is V, volt. Volt. So the unit is volt. V-O-L-T-S, volts. Then, or simply V, small letter V. Okay. Now, I believe you understand that potential difference. So we can say potential difference V now is directly proportional to current. Please take note of that. As we continue, I will refer you back to that. How do potential difference and current relate? How does potential difference relate with current? They are directly proportional. If one is increasing, the other also will increase. If voltage decreases, then current decreases. Okay, that is that. Okay, I believe you understand that. Now let's continue. There is another important parameter or physical quantities in electricity that you need to understand. That is electromotive force, or simply EMF. You use EMF, or you use simply capital letter E. Is that right? EMF, or simply capital letter E to denote electromotive force. Electromotive force is the total energy supplied by a source, like a battery or generator per unit charge. Let me explain that one. When I explain potential difference to you, I said it's like a push. Is the energy that causes the electron to move, work done per unit charge on electron between 2 points in the electric circuit. Okay, but electromotive force is also the potential difference. It's also the push. It's also the total energy. But in this case now, it is the total energy of the battery or any generator. Let me look at this battery. On this battery, on the side of it, what is written there is 1.5. You see they wrote 1.5 volts on this dry battery, this dry cell battery. What you wrote on it is 1.5. No, they wrote 1.5 volts on the battery. 1.5 volts on it. 1.5 volts. That's the total energy of a battery when it is not connected. This battery is not connected now. The total energy of this battery on this inside this battery, when it is not connected to external circuit, is called EMF, or electromotive force. So the total energy. So for this battery now, the total energy is 1.5. E is equals to 1.5 volts. That's total energy of a battery. So the total energy supplied by a source, it could be battery, it could be generator, and so that one is called EMF, total energy. So, and the difference between them, okay, yes, I'm going to explain the difference. So the difference between EMF and potential difference. Now, it is the maximum potential difference when no current is flowing. Yes. When no current is flowing, maximum potential difference. Maximum potential difference is the maximum potential. This, for example, this battery now, the maximum energy, maximum potential difference in it. You say potential difference is like push. But the maximum, when it is not connected, the total is called EMF. By the time it is connected now, yes, it will not be, part of it will have gone through, will have been used to push the charges through the circuit. It will not be 1.5 again. You understand? Okay. The unit is also volt. The unit is also volt because it's a maximum potential difference of a battery when it is not connected to circuits. When it is not connected to circuit, the maximum potential difference between the terminals of battery when it is not delivering current to external circuits is called electromotive force. You have not connected it to any conductor, to any wire. So the total energy when you have not connected it is known as electromotive force, or when the switch is off. When you connect the circuit and the switch is off, then it means it's an open circuit. No current is not flowing. Okay, we can say the total potential difference in an open circuit. But when you close the circuit through the switch or key, current will begin to flow again. Then we don't have, it is no more potential, it is no more EMF again. It becomes potential difference. Okay, now note the difference between EMF and the potential difference is that EMF is energy given by the source, while potential difference is energy used across the components. Energy used across the components. Let me show you something here from this diagram, from this circuit. Look at this circuit. Voltage is always connected across resistor. It's always connected across resistor, while ammeter is connected in series. Okay, this voltmeter here is reading the voltage in this circuit. Now look at the battery here. The EMF of this battery will be greater than the one read by voltmeter here. If in the battery here we have, as in the EMF of the battery here is 1.5, it can never be 1.5 here. Yes, why? I'm going to explain the reason why it cannot be 1.5 at this place, because part of it has been used. So that's why we say it is EMF is the energy given by the source, like this battery now, energy given. While the potential difference is the energy used across the components. The two are not the same. Why are they not the same? We are still going to explain later, but before then, let me quickly explain to you why they are not the same. There is what is called internal resistance. Internal resistance of a cell. The internal resistance is just like something that is in the material of this battery. Now, I'm using battery for example. the material of this battery will not allow this battery to give out 1.5 volts, its total energy. It will not give out its total energy because there is something inside here. It is called internal resistance of a cell. Every cell has internal resistance. The total energy here, the EMF is 1.5. But this cell, when connected, it will not give out the whole of 1.5 because of the internal resistance. So that internal resistance, let me give you in advance before we get there, is denoted by small letter r. Now, and there is going to be a voltage across it. The voltage across that small internal resistance is V small letter r. You see it? V then small letter r. That is the voltage across that resistance inside the battery. That will say you cannot go. For instance, so the total energy of a cell will equals to the one read by the voltmeter plus the one held back by the resistance of the battery. So the resistance of the battery, this one held by the resistance of the battery, is called loss voltage. It's called loss voltage. While this one is called voltage drop. Okay. Voltage across internal resistance of a battery is called lost voltage. Now, voltage across the one in the circuit, V capital letter R or ordinary V, is called voltage drop. So now electromotive force will now be voltage drop. Electromotive force here, E equals to voltage drop plus voltage loss. So I will explain internal resistance later. But I just want you to know why the voltage drop, this voltage read here will not equal to the one we have here. For instance, from this battery, if this battery we have 1.5 volts here, this one may read, the one inside this circuit now, the one inside this circuit can never be 1.5 because there is a material, there is an opposition, there is a restriction inside the battery itself that will not allow everything to go out. So there is an opposition in the material of the battery that will hold part of the voltage back, and that one is called voltage loss. So when you now add the voltage loss plus what you have here, it must equal to the electromotive force of the battery. Okay, so that is that about electromotive force. Electromotive force is the total energy of a battery. Look at this generator now. The generator, the total energy supplied by this generator is called electromotive force. This one too, battery. This battery is called electromotive force. But once you connect it, then the one inside the circuit is called potential difference or voltage drop. Just that. Okay. All right. So potential difference is energy used across components. Now let's look at another quantity, important quantity in electricity. That is resistance. From the word resist, it means oppose. Oppose. When something wants to move and you are preventing the flow, you are preventing the motion, it means you are resisting it. So resistance is the opposition offered to the flow of electric current in a material. Yes, and it is due to the material of that conductor. So there are some conductor, like there's some wires, that the material of that wire itself will not allow the electric current or the electric charge to move, to flow. If 20 is supposed to flow per second, they can reduce it to like 4. Yes, they can reduce it to 4. They can reduce it to 20 to 16. They can reduce it to 15. It varies like that. So it varies. So a wire of high resistance, these are the wire that's normally hot, normally become warm or become what, become hot, because when 20 ampere, let's say when 20 ampere of electric charge, 20 ampere of current, when if 20 current, electric, 20 ampere quantity of electricity supposed to pass, and the material of the wire is saying no, I can only allow 15 to pass. What will happen to the remaining 5 is that the energy of the remaining 5, because they are struggling to move, the energy will be converted to heat. That is why the wire become warm and become hot and melt. Okay, when it reaches the melting point, the wire will melt and break. So resistance is the opposition to the flow of electric charge in a material. It's resistance. No, I said something initially. I'm going to come back there now. That okay, we say voltage is proportional to current. The more the voltage, the more the current. This is an ideal situation. That is, if the material of that conductor, it will not impede, will not cause any resistance. If there is no resistance in the wire, then the voltage here, suppose if I supply 20, I supposed to get 20 here as current. If you understand how it's supposed to be. But because of the wire, the material of the wire itself, we will not allow it to be. So when we say voltage is proportional to current, when we now change the proportionality constant, voltage will now be IR. I don't want to write, I want to write I before R. So R is now the constant, is the constant of proportion. So R is called resistance. R is resistance. So that is how we come about this question. V equals to IR, and you see, you are going to get, when you make R the subject of the formula, so V equals to IR, then look at this formula here, R equals to V over I. Okay, it is from this formula, V equals to IR, and this is what is called Ohm's law. We are still going to I'm still going to explain that. So resistance is the opposition to the flow of electric current in a material. Take note of that. You know, when something is flowing, it's like tap of water now, as a water tap, the pipe. So if you put a device there that will not allow the current, the current to flow, maybe the volume of the water in the pipe is 20 cm cube, and there is a device inside the pipe that will only allow maybe 10 to come out. So that device that is restricting the motion, the flow of water, is called resistance, and it's called resistor. So what it does is resistance. The device itself is resistor. Let me give you an example of resistor. Look at this diagram. Look at resistor. Look at resistors. So this one, what is resistor used for? For instance, now, you know, we can, in our houses, in our homes, the electric supply there in those outlets is 220 volts. Now 220 volts, look at it, 220 volts, 220 volts, let me write 220 volts here, supplied. But do you know that your phone, maybe your handset, the one that your handset need to charge the battery, is just 7.5 volts. If it's more than 7.5, your phone will blow. So that is why inside the charger, inside the electric phone charger, we have resistor there. that will only allow only 7.5 to come out as an output. So that is what we only have. Okay, so that's what resistor does. It will resist the flow and only allow some. No, at times it will not allow. It will only allow some quantity to pass. So that is resistance, and the unit is ohms. The unit of resistance is ohms. So we have V in volts, I current, and R is in ohms. Please take note of this formula. R equals to V over I. V over I. Or when we're going to make V the subject of formula, V equals to IR. V equals to IR. So you make use of that formula. All right. Let's look at another. Yes, conductors and insulators. What are conductors? What are insulators? I told you that the material we have. I just explained resistance to you. That is the opposition to the flow of charges, and it varies. It depends on the material of the wire. You know, we have different type of materials. We have copper, we have gold, we have aluminium, we have different types of material. Okay, all right. Now, what is conductor? What are conductors? Conductors are materials that allow electricity to pass through them. We have some materials that allow electricity to pass through them, of course, like wire, like copper wire. So we have then example are metals, all metals. All metals we allow current to pass through them, copper wire. Water is especially salty or dirty water. Dirty water we allow when you pour water and there's a electric cable, open cable in the water, it's going to shock you. That is, it will conduct. Water conduct electricity, most usually salty water or dirty water. So, and what of insulators? Insulators are materials that do not allow electric current to pass through them. So examples are plastic, rubber, wood, dry air. So they use rubber to cover wires so that you can hold the electric cables. All those electric cables, you can hold them because they have already used insulator. Or the rubber cover is insulator. It will not allow it will not conduct electricity. So wires are covered with plastic because plastic is an insulator and keeps us safe from electric shock. You will not have electric shock because it's an insulator. Okay. So I think with this, yes, the last part of the class is factors affecting resistance. Factors affecting resistance. So what are the factors affecting resistance of a wire? Number one, length of the conductor. Longer length is more resistance. If the wire is very long, the more the length, the more the resistance. The more the resistance. Okay. So then number two is cross-sectional area. Thicker wire has less resistance. If the wire is thick, then the resistance will be reduced because if it is thick, the cross-sectional area is big, more it can accommodate more charges to flow. But if the wire is tiny, it will cut. The resistance will be high because by the time more charges want to flow through, it will cut, it will melt because the resistance is high. Okay, many of these charges will not be able to flow through, and in the process of trying to flow, the energy will be converted to heat and is going to cause the material to melt. Okay, now types of materials we have. Depend on the types of material, like copper. The purest one is gold, but you cannot see gold wire. Yes, almost zero resistance. Followed by copper. Copper has less resistance. Iron also have iron have, yes, copper has less than iron. So we have copper, we have iron, like that, silver, all those materials. So it depends on the material. These are the factors that affect the resistance of a wire. If the wire is copper, the resistance will be different from the one that is iron. Okay. Then another factor is temperature. Temperature. Higher temperature is more resistant. When the temperature of a conductor is high, resistance will be high. So these are the factors that affect the uh, resistance of a wire. We have four factors. Number one, length of the wire. Number two, cross-sectional area of the wire. Number three, type of the material. And number four, the temperature. So I want to believe you have gotten the whole thing. Don't forget the topic and where we started from. Potential difference as is a push, something that caused the electric charges to flow and so consequently cause the current to be produced. Without potential difference, no current. If potential difference is zero, current will be zero. Okay, they are directly proportional. And also we have electromotive force, which is the total energy of a battery when it is not connected to external circuit, when it's not connected to circuit, when it's not delivering current to circuit, to any external circuit. That is electromotive force, total energy, when it's not being used. Now, you have resistance. Resistance is an opposition to the flow of electric current in a material. And the material that does that is called resistor. Resistor. So in a circuit, if I want a particular quantity of electricity to get to a particular part of the circuit, I will use the appropriate resistor that will help me to resist and give me the number of current or the value of current that I need in that part of the circuit. Okay. Now, yes, I've forgotten to tell you, the symbol for resistor is this. Is this. Yes, we have two. Is either is this or is like boss like this. Yes. So these are resistance. The capital letter R is resistance. So what you are seeing here, this one is resistance. It's like this or like this. So that's a resistance. Okay, what you are seeing here is symbol of battery. Symbol of battery. The shorter one is negative terminal, while the long one is positive terminal. This one is key or switch. We have internal resistance. See this small letter R is the internal resistance of the battery that will not allow this battery to discharge all its energy. Okay, so that's internal resistance. I believe with this, you have grabbed the concept. Make sure that you do the needful by answering those questions I gave you under electricity. And if you have any question, you get across to me. God bless you. Until we meet, you have a great day.